Okay, you ready, Michelle?
Ready.
Okay, this battery right now has been sitting all night long. We charged it up yesterday. Okay, now after having sat all night long, it's sitting at 12.76. To it, we have this lamp, which is rated at 20 watts. And that ammeter. Get ready, you're going to have to turn it on, remember? You're my assistant.
I'm ready.
Okay, so we're going to have a look at what type of amp draw this light imposes on this battery and what happens to the running voltage. Not connected to the solar, just standalone. Okay, hit the switch, Books. Okay, so the light is on and we see that the battery is going to drop to whatever voltage plateau it wants to hold at. So we're watching it drop. Now we'll look at the amp draw, and it's not a full 20 watts. Well, I don't know. Not doing the math right now.
I'm ready to turn the switch off.
Okay, well, just wait 1 second. We have to get this on video, sweetie. Okay, so it's running at 1.5 amps, and it's holding around the 12.34 range or so. Now this is a fairly tired battery, but it's mostly seen Bedini charging, so it's doing pretty good for 2 years daily use. Cheap $25 battery from Walmart. Okay, so it's pretty fair to assume that it's probably going to hold around 12.3, 12.35, somewhere around there. Now what we're going to do is we're going to put it on the 20 watt energy light source from the sun, and we're going to run a 20 watt load on it. Now those of you who know solar panels, wattage is always overrated, and that's because charge controllers and batteries don't match the wattage of a solar panel real nice, because there's losses due to Ohm's law. For example, a solar panel that's rated at 100 watts is rated as such because under 20 volts it'll produce 5 amps. Problem is the 20 volts isn't utilized very well from the charge controller. So let's see what happens. I should say that in conventional, in an MPPT situation, it is substantially better. Now let's see what happens when we take this and we run the 20 watts on the same battery under the charge controller in good sun for several hours. Now, if we ready to shut off the lamp now, sweetie?
Yep.
Okay. Good job. You sure know what you're doing, don't you? Can you smile? Okay. So now we see that it's starting to recover. Okay. Just gonna hit it again, turn it back on. Good job. So there she goes, heading back down towards 12.3. Okay, so shut her off, Michelle. Perfect. So let's let this settle over a moment, and we'll call this our initial battery voltage.
I'm ready to turn the light on.
No, we don't need to turn it on. We gotta just see where the battery's gonna settle now. Let's see if it'll go to 12.6. Because we want to know what it's going to be at the end of the day. So I'm going to give this a little while to settle, and then while I hook it all up, we'll look at it once more before we fire up. So I'm going to pause now. Okay, so here we are set up. Same battery. Now it's had a few moments to relax, and can you see that? 12.8 is the voltage of the battery. I have this other meter which is reading 12.74, and it's going from the rectified side of the output of one transistor across to the negative. Okay, now the ammeter is simply the current draw on the, oh no, I gotta set this up correctly here. Oh, okay, no. What the ammeter is current going into the battery from the charge system. Okay? And now we're under full light. Okay, so when I start it up, we'll probably see that current slam, because these capacitors are probably sitting at 42 volts. Okay, so that's why the ammeter is going to go bang, which isn't good for the ammeter, but I've only got so many hands here to discharge and do whatnot. Okay, so we'll fire it up. Alright, so she's firing. So now we have 12.96 as our charging voltage, climbing a bit. Okay, and you'll see that climb for a bit. Okay, now I'm also partially shading the solar panels, which is a bit of a bummer. We're seeing a half an amp entering the battery, which is damn good when you consider that the theoretical maximum of one of these panels is 568 milliamps. Okay, and I'm partially shading them. I'm up over 500 now when I stand back just slightly, and you know, you're not going to see an amp out of this configuration because it's in series. Right now, here's my battery voltage under charge while charging. Remember that this battery was at 12.8 when we started. So let's fire on the 20 watt light or 18 watt light. Okay, so we see the battery voltage drop, which should be concurrent with a loss of energy, which would make sense. It's pulling almost an amp and a half, and we're giving it only a half an amp. So that's that. We're looking at 12.75 on the battery. We're still seeing a charging current of a half an amp, and that's our potential measurement. Okay, so that's, you know, basically just reading battery voltage at this point. We cannot see a higher potential right now because the battery is not resisting charge, which you wouldn't expect it to do when it's under a 20 watt load. You see that thing start resisting a charge, like when you're desulfating, you're going to see this number climb, but not right now. Okay, it's going to be very close to battery voltage. All right. Okay, so now the idea is we just leave it and see what happens. Can we run this the better part of the day and still see a battery that rests overnight and relaxes at 12.8 in the morning? Well, 12.7 something like it was. The answer has got to be no. I mean, we're pulling an amp and a half, and we're imposing a voltage drop. Now, when I was playing around with it yesterday, I didn't see a loss of energy, but I didn't do it long enough to really tell. But what I saw was a very strange anomaly, whereas that number right there that you're looking at started to climb. You shouldn't climb. You should drop steadily all day. Okay? Because you're pulling more current than you're producing. But it's close. We're not in huge margin here. So this is just for fun. But see, when it comes to radiant energy, how do you determine whether you're getting some, right? Well, a battery that was under load, pulling more current than it was pushing, if it was imposed with a radiant energy charging effect, you might see it this way. I'm not saying this is the way to do it, but you might see something that was out of the normal. After 4 hours of run time, we should see a drop at least of 2 to 3 points on that voltage. This should, by tomorrow morning, having sat there, this battery should be no higher than 12.4 or 12.5 after running this for several hours. So I'll take note of the time now and figure out how long it's ran for, but we're going to let it run for a long time here while we got good sun. Alright, so we'll leave it at that, and I'll add to this in a while. Okay, so here we are an hour later. It's like noon, about 11 we started. We got full excellent sun, so it's really good for the test. Now I think I was sort of kidding myself when I thought it was charging and running the load at the same time. It's so difficult with solar because you have an ever-changing amount of energy coming in, and it can fool you. You think, okay, full sun is full sun, it's going to be the same all the time. Well, not at all. Anyways, my operational voltage has increased, more likely is what's going on. But there are still some interesting things happening. There's so many things happening simultaneously when I do this type of experiment. Okay, so now our operational voltage is 12.57. Okay, or climbing to 12.57. So it's very ambiguous as to whether our operational voltage is changing or whether the battery is actually charging, because we were sitting at about 12.5 when we first started, but the sun's getting more intense. Lots of different things are going on. Here's one little interesting thing, and I don't know what all of is involved here. I'm just playing around with it. But you can see that we've got almost 500 milliamps of current going into the system right now. Now, it is interesting, the behavior of this, and I'm sure this would probably be much the same in most solar charging environments, but it's interesting how you can see the load is still on. What happens with the incoming current when I turn the load off? Okay, so let's just turn the load off momentarily here and watch these numbers. Okay, so now our battery is climbing to a new charging voltage. Okay. And I'm not seeing the same effect that I saw. What I saw before was my incoming amps go down. Okay, so I'm going to switch the load on and off, and let's see if we can see this effect. Not so much anymore. A little bit. What I'm seeing, oh, I think that's what happened was I just got a dip. So it's messing with the oscillations. I thought it was actually putting a lot more energy into the battery while the load was running, but I think what happened was it dropped because the oscillations fell out of oscillation completely for a moment. But with that additional resistor in this circuit, it's all automatic, right? And that's one nice part though, because if a very dark cloud, which often happens here, we get thunderstorm clouds, so you can have a brilliantly hot sunny day and then a black cloud rolls over. For a moment the sun just drops, and that really messes with trying to keep an oscillator running. Okay, so anyway, let's just have a look at that again. Okay. And we're going to shut this system right down and just have a look at the battery voltage after having run for an hour. Okay. So this is completely shut down. There's no energy going in. Our battery, or our cap voltage will probably be up to about 42 volts now. So this is strictly battery voltage trying to stabilize. Now we started at 12.8 or 12.79, somewhere around there. So we have dropped some. Not much though. And to me, the interesting part is that I know I have the next thing to 1.5 amps going out, and I only have 0.5 amp going in. So what I want to see is a profound loss in this battery over a duration of time. And I'm not really seeing it. I'm seeing a climbing operational voltage and only a small energy loss, which is a little odd, but you know, it'll prove itself one way or the other. You know, granted, the amps going in is at a higher potential than the amps going out, so there's a little bit of a mess with your head there a little bit. The watts is probably fairly comparable. Okay, I'll come back in an hour or two. Okay, so here we are back. This has been running for 4 hours now, and kind of shot down my theory that it would be charging in addition to running a load, because I've seen that number as high as 12.57 running voltage, and I hope you can see that, but it's 12.53 now, so obviously we're not gaining. But considering that we know the lamp draws the next thing to 1.5 amps, and the meter's showing 0.5 amp, the question is, how much have we lost? If that's approximately a 20 amp hour battery under 1.5 amp load under normal circumstances with no input, you'd expect that after 4 hours you'd lose somewhere around 0.6 of a volt off of your battery. That was, you know, what I would calculate as being approximately what you would see as a loss. Now, of course, if you were imparting 20 watts the entire time, or 18, 20 watts the entire time, you'd expect no loss. You'd be, you know, breaking even. So where do we sit? You know, granted, the whole point is if you're only putting 500 milliamps of current into the battery and you have an excess voltage, are you losing or doing as good as you would with them parallel? Okay, Boogs, back up there. I need you, assistant. Okay, I want you to turn the lamp off, sweetie. Alright, so now the lamp's off. Okay, and let's see what happens to our voltage. Now, I have no idea whether you can read this, but it's climbing 12.68, 69, 7, 12.7. Now, of course, we're still under charge here. We're charging, I should say. Okay, Michelle, don't put your face too close there. Okay, so we're charging 12.75. Okay, so now let's disconnect the charging circuit. And where will the battery come to a final rest? Looking good so far. It was about 12.78 or 9 when we started. Essentially, we're still looking at what looks like so far a charged battery. Now, part of the point is that some people might look at this circuit and say, well, it's a complete waste. You've got way more voltage than you need. You're running 41 volts, 500 milliamps, let's say. But is this system capable of utilizing that? I think it is pretty close, you know. It's a completely unconventional setup, but given the larger capacitance and the nature of the locking oscillator circuit, it seems at this point to do a pretty darn good job of taking the excess voltage and putting that into charging current. What are you doing there, Books?
I'm standing up.
Yeah?
Yeah.
Are you part of the show?
Yeah.
Let's have a smile. Do you like batteries? What's your favorite part about batteries and solar panels?
Electricities.
Yeah. Free power, right?
Right.
Okay. Yeah. So we'll have a look in a little while and see where this is going with a standing voltage. So far it's sitting at 12.69. Let's see how far it'll drop. Okay, so here we are, about 45 minutes. We've given time to settle. Now, if you followed me from the beginning of the video, there was one confusing thing, and that is that I switched meters and they didn't really agree. The one meter said the starting voltage of this battery was about 12.74, and the other meter said that it was about 12.8. So for argument's sake, I have both hooked up to the battery right now, with the battery doing nothing. The one that said its starting voltage was 12.8 is reading 12.71, and the one that said that its starting voltage was around 12.76, I believe, is now showing 12.64. So there you have it. I've lost approximately 0.1 of a volt over 4 hours of running a 20 watt load with 20 watts worth of energy coming in. But in my mind, that's pretty good, and what it's done is it's proven to me that I can have an 1.5 amp imposed load and have only 500 milliamps of current coming in, but have the watts that are produced doing their job. In other words, the energy is stored in the capacitors, and the energy is eventually utilized and not lost due to Ohm's law. Okay, and in this particular situation, that's kind of neat, because I would like to compare it, and I probably will, with the exact same scenario using a pulse width modulator. Now, in the case of running a pond pump, for example, or something, that would be pretty neat, because rather than having the charge controller sit there at float, it'll remain high, and the extra voltage doesn't seem to be at a complete loss. So it was worthwhile. I don't see any free energy, but I see an interesting situation, and thanks for watching.